This is lesson 66 of the quantum mechanics, a mini lecture series titled Commutators. Now, in quantum mechanics calculations, one often comes across commutators. Okay, and if you recall, this is what Heisenberg came across whilst trying to formulate his version of quantum mechanics. Okay, namely matrix mechanics. And so, a commutator is basically a mathematical operation that determines whether or not a pair of quantities satisfy the commutation relation. So, putting this into context, in the classical case, we know from basic maths that A times B is the same thing as B times A, right? If I do 1 times 2, in other words, it's the same thing as 2 times 1. Okay, because the product AB, right, this is AB, is the same as BA, right? In other words, the order doesn't matter for when it comes to multiplying the numbers A and B. Okay, they're mathematically equivalent in the classical sense. When we hop into quantum land, however, we find that this isn't necessarily the case. In quantum mechanics, AB doesn't necessarily equal BA. Okay, and the standard notation for writing a commutator is as follows, right? So suppose I have two operators corresponding to two observables. Okay, an observable, if you remember, is something which you can measure, like position or momentum of a particle, for example. And I wanted to find their commutator. So let's suppose I have position. Operator for position is an X with a hat. Let's say momentum in the X direction. I'll do this by using square brackets as follows. Square brackets separated by a comma. Okay, this is the position operator. This is the momentum operator in the X direction. Now, the next step in determining the commutator is simply take the product of the first quantity with the second quantity minus the product of the second quantity and the first quantity. In other words, this is equal to operator X multiplied by P sub X minus P sub X multiplied by X hat. All right, it's as simple as that. And this isn't actually equal to 0. It's not equal to 0. If you do the maths, if you plug in what X and P sub X are, you'll find that it's actually equal to minus I H bar. Okay, it's not equal to 0. Whereas in the classical case, suppose I have 1 and 2. The commutator of this is just 1 times 2 minus 2 times 1. It's 2 minus 2, that's 0. Right. As an exercise, try and find the commutator of 3 and 4. Let's see what you get. And that's the idea of commutators.